although you, although you're going to learn a lot regarding things like the unit circle in your pre-calc class and stuff, a lot of what math tends to do is procedural and tries to do things the same way all the time. One of the things math has done is kind of indicated that when you go around the Cartesian coordinate system, I wouldn't write this down if I were you. You get things like 0, 90 degrees, 180, and 270. As you advance with unit circle work, they'll name these things like pi halves, pi, 3 pi halves, and 2 pi. The problem is that doesn't really work for everything, because in other kinds of measures, we make this one north, right? Which would make this west, and this east, and this south. But north is also associated with 0 degrees. So we already have a problem, right? Math wants to the right to be 0, and every map wants upwards to be 0. To make matters worse, east is 90 degrees. South is 180, and west is 270. Do you see a difference in the way it's done? One goes clockwise, the other one goes counterclockwise. The truth is, it doesn't matter. You just need to know which one you're working in. Does that make sense? Now, math is going to force you to always make 0 to the right, and that actually screws us up for actual use of trig in this class. So, for us and this unit, we're going to go with our standard measures of direction. We're going to talk about everything relative to north, south, east, and west. I want you to draw the following vector. Graphically, a vector is just an arrow that starts from the origin and points away from it and has whatever qualities we set upon it. This is going to be a displacement vector of 6 centimeters, 40 degrees east of north. Now, I'm of the impression that some of you don't know how to use a protractor because you told me you don't know how to use a protractor. Some protractor idiots, I guess. Frigidiots? There's got to be a phrase there. But let's put that aside for a moment. I don't know that you know where to put 40 degrees east of north. So if you're concerned or you don't know, when I say 40 degrees east of north, you're going to be starting with a vector that is to the north. And then you will rotate that vector 40 degrees to the east. So you need to measure an angle that is 40 degrees to the east from the north. And then draw a 6 centimeter line to represent that vector. If you don't know how to use your protractor, please ask. But let's see, that took 15 minutes and I got a whole 3 minutes of instruction in. It's okay. The next one's going to be easier. I'd like you to draw a second vector. I want you to imagine that these are instructions, that you're being told to walk this path. Like you're going to walk 60 meters, at this direction, and you're going to turn and walk another direction. So the next one I want it to be 3 centimeters due east. Now to do this, you start here and draw your new vector from the tip of the old vector. That will mean making a small, maybe reference set of lines that you know are vertical and horizontal, so you can make sure that when you draw this, you are being accurate. This one should have been easy, as you didn't really have to use a protractor this time. So your protractor skills were not put to the test, luckily.
Are we gonna have a protractor for this?
No, my heart couldn't take it. All right, once you're done, the idea of what we're doing today is about the sum of vectors. What you're doing right now is a graphical sum of vectors, meaning if you're doing everything nice and to scale, the solution is an arrow drawn from the origin to the tip of the last vector. This would be called the resulting sum. Solving sum of vectors graphically is almost as accurate as doing it mathematically. If you're careful with your drawing and the angles aren't particularly tough, you can usually get pretty good results. Pilots used to do this all the time in the cockpit while flying to adjust for wind and keep their heading straight. So this is not something that is a skill that's not even currently used. If you want to get a pilot's license, you have to learn how to do this graphically anyways. And they have tools that help them, but the whole point is that they're able to make sure they can point the plane in the right direction against the wind to make sure that they are flying in the right direction compared to the ground. Now, you have to be able to do sum of vectors. It's what our next topic is. And I want you to be able to do it both graphically, like we've just done, and mathematically. The problem is that the mathematical version of this can be kind of challenging. So I want to talk about how you solve things mathematically. Now, to put this into context, this is part of Unit 1.2, two-dimensional motion, specifically sum of vectors. We'll have a couple things we're going to lump into two-dimensional motion. Sum of vectors is one, projectile motion is another, and something called uniform circular motion. So you guys prepared? You ready for the next part? We don't have mathematics that allows us to add two-dimensional vectors together. These are considered two-dimensional vectors. The problem is our math only allows us to work in one dimension at a time. This representation is called polar notation. And it specifies a vector as a length, a velocity, or an acceleration, and a direction. We can't actually add these together. But if we want to add the vectors, there is a method that will let us do it. But to do so, we have to convert these vectors to rectangular. Rectangular notation takes a single vector and splits it into two component vectors. Although you've done rectangular notation before, you probably didn't have it called this way. But again, rectangular notation takes a single vector, like this one, and breaks it up into a part that's in the x direction and a part that's in the y direction. It splits our vector into components. That's a vocabulary word, one you're going to have to know. Component vectors are two right-angled vectors that represent a polar vector. Component vectors are two right-angled vectors that represent another vector, a polar vector. I want to show you how to do this. And it's going to seem laborious, and it is. This is a time-consuming process. But we have no choice, as we have no other math that can do this for us. So we're going to start by taking the vector we just drew and break it up into polar notation. So I'm going to look at just that vector. Now, I'm drawing this because I need something that I think is a good visual aid. It would probably behoove you to draw this too. Just a piece of scratch on that same paper where you're drawing stuff. But we're only going to draw one vector here at a time. And the vector we're going to draw is the one that is 6 centimeters, 40 degrees east of north. You don't have to draw this accurately, as we're not going to take measurements like this. We're going to do the mathematical part. If you did draw it accurately, we probably could just measure the sides of the triangle. But that's probably not what we're going to have to do. So this is 40, this is 6. Now, before we go any further, do you see an implied triangle? Good, good. I'm glad that you do. I do too. I think there's either one here or one there. It doesn't matter which one of these we choose, except we were given the 40 degrees. So I think it probably makes sense that we use that one, right? So I'm going to leave this triangle as the one we're going to use. And then I want you to consider that if we're using that triangle, the components will be this side and this side, as they represent the original vector. Now you have a set of steps that you learned yesterday that can tell you what the x component's going to be and the y component's going to be. Can you follow up with those real quick and figure those out? They're on the board over there. They're written really small, but I'm sure you made your own set of notes to help you out. We have limits on time, so I put the answers up there, but you should be endeavoring to see that you can do this. Just putting them up there so you can check your work. I will help in that I will go through the process that's already on the board, okay? So I will identify the angle of focus, which is going to be the 40 degrees. You get rid of what's here so that we're not distracted by it. I will identify the sides based on that angle. So I have opposite, adjacent, hypotenuse. I'll write out my functions, which will start with sine 40, which equals opposite over hypotenuse, which is 6. Cosine 40, which will be adjacent over hypotenuse, which is 6. And tangent 40, which is opposite over adjacent. This is the branch where I have the angle. So since I have the angle, I can compute the sine, cosine, and tangent of 40. So the sine of 40 is 0.64278. 0.64278. The cosine of 40 is 0.76604. And the tan of 40, which I'm not going to need, is 0.8391. Now it seems like I can figure out the opposite side directly by multiplying both sides by 6. So 6 times 0.64278 is 3.857. The adjacent side, I can do the same by multiplying both sides by 6. So 6 times 0.76604. 0.4596. I'm sorry, 4.596. All right, we have found the two sides. Think we're good. So now we've used the triangle stuff to find the sides. We want to write this as a vector, which means writing this in its rectangular component form, which will be 3.857 in the x direction. That x with a hat on it is a sign to me from you that says this is how much the vector is in the x direction, plus 4.596 in the y direction. That is successfully taking our vector and converting it to rectangular notation. We've broken it up into its components. All right? Now you have to do this for every vector you're given. So we have another vector, 3 centimeters due east. Now luckily this one is due east, so is there any component in the y direction? No, so we can just write this as 3x hat plus 0 y hat. So that's step 1. Convert all polar vectors to rectangular components. Step 2. Add like components. This part's the easy part. Just add them. So quite literally, 4.596 plus 0. $3.857 plus 3. Step 3, convert back to polar. Now, converting back to polar, again, I'm going to try and do this in a manner that is very clear. I'm going to put a quick Cartesian system here, so I have something as reference. And you guys who are just learning to do this, I would spend time. I would use the paper. If you're on a tablet, it's even easier. You just want to give yourself something that can easily show what it is you're doing. We have 2 sets of instructions here. Go 6.8 in the x direction and 4.6 in the y direction. So 6.8 in the x direction, 6.857. And then 4.596 in the y direction. Always display your vectors tip to tail. Always start the first one at the origin and start the next one at the end of the first one. Those are our component vectors. Do you see an implied triangle? All right, so we have an implied triangle. Right there. We want to find the result. and we want to find the angle. Do you have a toolkit that could bring you to do that? Alrighty, give it a try. But we only have a few minutes, so I think you're going to need to hurry. We can get the length pretty easy because you can use the Pythagorean theorem. So you may want to do that. It saves you time. So I'm going to do that first. I'm going to label my sides so I know what's what. This is opposite. This is adjacent. This is hypotenuse. I'm going to consider the trig functions. Sine theta is opposite divided by hypotenuse. Cosine theta is adjacent divided by hypotenuse. And tangent theta is opposite divided by adjacent. Seems pretty clear that with the information I have, it'd be best to use tangent because it's based on the information that is the most rock solid. Anything I've used those numbers for makes it more and more fuzzy. So 4.596 divided by 6.857 gives me 0.67026. So tangent theta equals 0.67026. Well, I want to find theta, so I need to take the inverse tangent of that number. Gives me 33.8 degrees. How we doing, everybody? Everything okay? Well, this is what you got to do. I'm talking it all out. What's the troubles? Got 6 minutes. You want to ask some questions? Now's a good time. Yeah. How'd I get which one? I got the hypotenuse by doing 4.596 squared plus 6.857 squared and set that equal to the hypotenuse squared. I used the Pythagorean theorem. I didn't have to. I showed you guys yesterday that once I have the angle, I could plug that back in here. But Pythagoras works. So there's no reason not to use it.
But if you didn't do that, you would take those two and put it into the.
Yep. Yeah, that's exactly what I would do. Go ahead.
So you added 3 to the x and 0 to the y. Is that because in the beginning you moved these 3 centimeters?
Yes. And I'm trying to add the two vectors together. So I converted both vectors to rectangular, and then I added the like components. Okay? All right. I would love to say we're done, but there's one final thing you must do. When you reach the end, you actually have to write your vector in a form that tells the length of the vector and gives the direction with appropriate reference. So although the length of the vector is 8.25 centimeters, my reference has to include the angle and compare it to one of the directions. So our angle is compared to east. So starting at the east, I have to move north 33.8 degrees. So we would say that our angle is 33.8 degrees to the north of the east. Now, look at the one you drew way back at the very beginning. Measure how long it is. It should be about 8 and a little bit extra. If you're careful, it works out really close.